Welcome. Now, today is lecture number 42. See, make a note. Part 3, briefly, part 3 of part 3 is what? You can write centroid and moment of inertia. Every day you can see it there. Lecture number 40 is starting of moment of inertia, introduction and principles required for everybody. But lecture number 41, that is previous class, this is exclusively for those who want to gain a thorough knowledge about moment of inertia. As I told you, how to understand what is actually moment of inertia and how to feel it. See, when you look at a member cross-section, member cross-section, that moment of inertia, feeling should come. I told about dispersion, so many things in the last class, lengthy class. So those who are not serious about all these things, they can skip that one. But remember, now, today, lecture number 42. Now it is required for everybody. I am continuing. Actually, from 40, you jump to 42. Those who are not too much serious about all those basic concepts, or they will feel these are all, I find difficulty. Okay, leave it. So from 40, you go to 42, today's class. Now, today's class, what I will do is, I will cover two important theorems connected with area moment of inertia. Okay, now onwards, remember, I won't waste time. Now onwards, if I write moment of inertia, it is for area or lamina or cross-section of a member. We are not discussing mass moment of inertia here. I already told it. That's all. So, two important theorems connected with area moment of inertia. First one is parallel axis theorem. Remember, see, I wrote a little bigger here. Second one is perpendicular axis theorem. Now remember, parallel axis theorem is the most powerful theorem among the two. If you give weightage as far as application is concerned, I will tell you weightage point of view, 99%, 1%. That's all. 99%, 1%. Now, something I will tell you. Today, I will not discuss too much about the principle. I will tell you too much details about the parallel axis theorem. I will state the theorem. Of course, I will write before recording because by lengthy theorem. I will state the theorem, give some explanation, and then prove the theorem. Prove it. Once I finish that one, I will go to perpendicular axis theorem. Again, state it, explain it briefly, and prove it. That is sufficient for ordinary people. But after these two theorems are over, one more class, next class will be some extra terms are there, like radius of gyration or polar, one term called polar moment of inertia. It will partially come today only. And then something called product of inertia. They all will be discussed in one particular class. I don't know exact class number. Then we will go for derive expressions for moment of inertia for standard cases, rectangle, triangle, circle, semicircle, quadrant of a circle, all those we will start deriving. And make a note, once we finish all the basic explanation, then when we enter numericals, plenty of numericals, remember, like centroid, you know it, how many numericals are done. When you enter numericals, everywhere parallel axis theorem will come. It will follow. For that matter, during the entire structural engineering, wherever you go, this will not come. This will come only for torsion. That too, we are studying torsion for circular shaft. Polar moment of inertia is pi d power 4 by 64 for solid, pi d power 4 by 32. 64 is for rectangular. Pi d power 4 by 32 for circular cross-section, and pi by 32 into outer diameter power 4 minus inner diameter power 4 for hollow. That's all you require. So we will not here. We will Because see, but subject point of view important. So we will state it, prove it, and then use it somewhere, and then almost forget it. But this one, wherever you go, it will follow you. And during the numericals, everywhere you have to use parallel axis theorem. So now what I will do is, first I will take parallel axis theorem, statement and explanation and proof. Once I finish, today only, I will finish perpendicular axis theorem. Start now. First go to parallel axis theorem. Statement. I wrote a lengthy statement so that some people, usually they condense it. This much nobody will write. See, this much statement nobody will write. I will tell what people usually will write. Moment of inertia of an area about any axis is equal to sum of moment of inertia of that area about axis, centroidal axis, parallel to that axis, and product of area and square of the distance between the two axes or perpendicular distance from centroid to that axis. That's all they write. But I am making fully clear. What I told, just leave it. Moment of inertia of an area. Any area, see. Some area, A. About any axis. Here, any axis means, I will tell you a little later, see, that any axis here means either AB or CD or EF. EF also will do. One horizontal I taken, one vertical, one inclined. See, there is no rule that this AB centroidal axis for cross section like that. Centroid is here. About any axis, but very important, lying in the plane of the area. See, this is the area plane. The axis should lie in the plane of the area. Plane of the area is equal to sum. Sum means plus. Okay. Two terms are there. See, I have to understand now. Plus. Two terms are there. The first term is, I will underline now. See, the first term is this one. This is to make more clear. This is to understand. Otherwise, sometimes confusion will come. This is the first term. See. Little lengthy. And, see, and means plus, second one. Second term is, see, this is to understand. Otherwise, sometimes people get confusion about this language. See, this way I am doing only for understanding. You should not do this way if you are writing an examination like that. 1 minute now. Let me check the camera once, first of all. I hope it is not below the camera. No, nothing worry. Okay, see now. The moment of inertia of an area. See, area. About any axis. Here any axis means, when I go to explanation, either AB or CD or EF, that you will worry later. About any axis. But very important, that axis should lie in the plane of the area. You cannot take an axis like this. Is equal to sum. Sum means two terms are there. So first term is, see, you write that way. The first term is what all I wrote dot 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 dot. Second term is, see, the second term is, which I underlined lightly like this. Okay, this way. Sum of moment of inertia of that area, say this area, about an axis lying in the plane of the area, not something like this, plane of the area, and passing through centroid of the area. See, come to centroid. Through the centroid, see, suppose you want AB or CD or EF, come to centroid. Find moment of inertia about an axis lying in the plane of the area and passing through centroid, and not only over area, and parallel to the axis about which moment of inertia is required. That means If you want moment of inertia about AB, your axis should be parallel to AB. If you want moment of inertia about CD, axis should be centroidal axis should be parallel to CD. In case you want moment of inertia about EF, the centroidal axis should be parallel to EF. That I will explain once again now. So that one, and means here, and plus. See, I told sum of, this is the first term, and second term. The product means multiplied by product. See, product is product of that area, whatever is that area, and see, and means area, and means product of area, and means multiplied by the square of the perpendicular distance from centroid of that area to the axis about which moment of inertia is required. Means product of what? Area and some perpendicular distance square. So if you want I about AB, product of area and this distance square. If you want about CD, this distance square. If you want EF, it is this distance square. This is the statement. Now I will explain thoroughly all the three, only for understanding. But for proof, we will take one of the axes. We see now explanation. You go through this again and again, or little later, one exclusive class will be there for application of moment of inertia using parallel axis theorem. Remember, once again will be around 2 hours class. Very exclusive class, so that your complete confusion for finding moment of inertia is removed on that class. I will tell you, number one critical class for understanding, not feeling or understanding the meaning of moment of inertia. For finding moment, some will tell, yes sir, that's what we want. See, theory part, okay, we will sometime forget, but calculation part, for solving problems, that time, around minimum 2 hours, I will take a rectangle, a triangle, semicircle, circle, quadrant, everything I will place. Once I will find for this way axis, once I find for this way, explain each and everything at that time. One I will write there, one exclusive class for 100% grip on parallel axis theorem. So at that time. Now this I will remove. Anyway, you can take a screenshot. If you get doubt at any stage, you see the statement. See the statement. Okay, now I will explain. This I will remove. I will come here. This is there. Okay. Some statements you have to write. Consider area A. See, area A. Next, let G be centroid for that area. You should write it. I am not writing. Those who are serious should write. G, right now capital G, capital A. When you go to application later, I will change it over to small a and small g. I will tell the reason later. Right now, don't worry. Next, consider area A, consider a lamina of area A for which G is the centroid. Then, let us, now we have, suppose we have to find moment of inertia. See, suppose we have to find, I should short form, moment of inertia of that given area about one axis AB, comma, CD and EF. Remember, separately, not in a single step, separately, by using parallel axis theorem. What you write is, from centroid here, drop perpendicular to AB. See, H is perpendicular from centroid to axis AB. See, HAB. HCD is from G centroid perpendicular to CD. HEF. This much you write. Now start. Suppose moment of inertia of given area is required about the axis AB exclusively. See here. About, right now AB is black color. Little later I am using red color for that one. That all you do when you do problem. See, now, area is here. Some will tell, not same shape. Okay, don't worry about it. I cannot write the, see, zigzag, I can't write once again here. Who will remember how the shape? I cannot see turning. See, randomly written area, some area. Area is A. Centroid is G. Okay, now, if you want moment of inertia about AB, see, this axis, you write here. First, you consider an axis. You should, all this you have to write what I am dictating. If you want moment of inertia about the axis AB, see here, first you consider an axis passing through centroid and parallel to AB. So this is centroidal axis of the given area parallel to AB. See, this way. Okay. Then, according to parallel axis theorem, I about AB equal to I about the centroidal axis, IG. IG means moment of inertia about centroidal. Which centroidal axis? See, IG about this axis. I told, this is a statement there. I about the centroidal axis parallel to AB. This IG is I about this axis. IG plus area into square of the perpendicular distance into HAB square. This is later very thoroughly I will explain. Okay, over. Now next write. Everything over. Suppose moment of inertia of the given area is required about axis CD. Okay, CD. So imagine CD is here. This is CD. Remove AB. I should remove AB now. AB is not there now. See, this axis. Okay, then CD. Then CD is here. First come to centroid. Draw an axis. So this is centroidal axis. See, I can do one thing, save the time. See. Okay. This is centroidal axis of the given area parallel to CD. And from centroid to CD, draw perpendicular. Perpendicular. Say HCD. HCD. From centroid G, drop a perpendicular to axis CD, about which moment of inertia required. Then, according to parallel axis theorem, ICD equal to once again IG plus HCD square. H for CD square. IG means about which axis? See, this IG is, you write here, this IG is about, this you can write here, this IG is about this axis. Which axis? This axis. So, see, if you want I about CD, it is moment of inertia about centroidal axis parallel to CD but passing to centroid, I about this axis plus area into this distance square. Okay, then write. Lastly, suppose moment of inertia of the A required about EF axis. EF. Everything patiently you are write. Okay. Then your EF is where? I don't know where is EF. Okay. See, EF is somewhere here. EF. This is axis about which moment of inertia is required. If I have not written earlier, you write earlier, forgot. When I wrote AB here, you write, just add one more statement there. If I have not written, when I wrote AB here, you write there. Actually, already there. When I explained AB, you write there. Axis about which moment of inertia is required using parallel axis theorem. When I wrote CD, right here, axis about which moment of inertia is required using parallel axis theorem. Now write axis about which moment of inertia is required. Now, see, centroid is here. What you do? To the EF parallel axis. This is a centroidal axis of given area parallel to EF. See, if you want about EF axis, come to centroid, consider an axis parallel. Then from here, draw perpendicular. HEF. So perpendicular. Now, this is what? This is perpendicular distance from centroid of given area to EF about which moment of inertia is required. Then, according to parallel axis theorem, IEF equal to once again IG. IG means what? Moment of inertia about centroidal axis. This is moment of inertia about this axis. That IG is, if you want about EF, IG means about this axis plus area into HEF square is about EF. This is sufficient. Okay, now I will go for proof. Anyway, I am not telling too much because later I told more than 2 hours. It may take 3 hours also. A marathon class will be there. That I will tell you required for everybody. Yesterday's class I told required for those who are doing concept, those who want concept. But that class I will tell required for everybody, those who want to solve problems. I'll go to proof. Now, proof for parallel axis theorem. See, some statement you have to write. I will dictate. Consider an area A. Let G be the centroid. Then, consider any axis AB lying in the plane of the area about which moment of inertia is required. You write that way. AB is, you should write here, see, AB is the axis about which moment of inertia is required using parallel axis theorem. See, draw perpendicular to GAB, axis AB, I write here, about which moment of inertia of given area is required. Now, see, from centroid G, draw perpendicular to H, no HAB, simply H to AB. Only one H is coming. Now, then write, also consider an axis passing to centroid and parallel to AB, that is centroidal axis passing through G and parallel to AB. AB is, you can write here, once again if you want, AB is right here, axis about which moment of inertia of the given area is required. Then, by parallel axis theorem, I already told you, IAB equal to I about the centroidal axis IG plus area into H square. This is to be proved now. This is I wrote as per parallel axis theorem. This is the result. Now we will prove it. See, what you do is, first consider, go back. Very simple proof. First, consider elemental area dA. Very small area, dA. Let Y be perpendicular distance from dA to centroidal axis. See, to centroidal axis parallel to AB. So, dA is the elemental area. Let it be Y. Then, leave it. By basic definition of moment of inertia, if you want IAB, what is the theorem I told? Basic definition, moment of inertia of an elemental area, if you want, it is summation sigma of product of elemental area and perpendicular distance from the elemental area dA to the required axis. So, if you want I about AB, it is elemental area dA into, see, If you want about AB, from here to here, see this is a green color, to AB, y plus h whole square. Area, elemental area into square of the perpendicular distance from the elemental area to the required axis. Okay. Now, class, I already told you, basic definition, equal to sigma of dA into y square plus sigma of dA into h square plus dA into 2hy sigma. This is a plus b whole square, a square plus b square plus 2ab, everywhere dA outside, or equal to, simplify, sigma dA y square, write as it is. Here, h is a constant. See, y, dA and y are variable. H is constant. Take h outside. H square into sigma dA plus here 2h outside into sigma dA y. Now, see correctly, right? Sigma dA y square is equal to what? Ig by basic definition. Basic definition. By basic definition of moment of inertia. Or I'll put I black, Ig. Okay, black color is there, okay. Is Ig. Why? Because, don't see here. If you want moment of inertia about the centroidal axis, it is dA into y square sigma. About AB, if you want dA into y plus h whole square. But when you want about centroidal axis, it is area into y square sigma Ig. Ig means moment of inertia. You write here, moment of inertia about the centroidal axis parallel to AB. Then sigma dA is nothing but, everybody knows, only sigma dA is nothing but total area A. Very easy to understand, summation of only area. Now, for students, I will tell, those who are studying engineering mechanics, exam point of view, I will tell them, see, we have to prove IAB equal to Ig plus AH square. You already got IAB equal to Ig plus A into H square. Yes, yes sir. So this term is unwanted term. You write, we know that sigma dAy equal to 0. I will tell them, why you don't bother, examination permitted. We know that. It is very clear, crystal clear that sigma dAy into 0. But I will tell you why sigma dAy is 0. Next, lastly, see correctly. Sigma dAy is what? Is moment of the, first moment of the area about centroidal axis. Is first moment of the area, first moment of area about centroidal axis. Centroidal axis. Or, remember, or you can write sigma dAy divided by area will give y bar. See, basic definition right here. Basic definition of centroid. Basic definition of centroid. So many problems are solved there. Sigma dAy by area is y bar. Y bar is distance of centroid of given area from where you consider y. We are considering y from centroidal axis. From centroidal axis. Oh, distance of centroid from centroidal axis. Therefore, surely y bar equal to 0. Area cannot be 0. Therefore, sigma dA into y equal to 0. Or you can do one more thing. If you have got interest, sigma dAy is moment of the entire area about centroidal axis. Moment of the entire area about centroidal axis equal to entire area into distance of centroid of the area from centroidal axis. Distance of entire area from area lies, distance of the centroid of the entire area lies in centroidal axis. Therefore, 0, 4. Therefore, right here. Therefore, what you got? See, Therefore, your IAB equal to what you got result now. Therefore, right, IAB equal to IG plus A into H square. A into H square right here. That is parallel axis theorem is proved. Right here. Parallel axis theorem is proved. Okay, sufficient. Now, I will go to next perpendicular axis theorem. Today only I will finish it. Not much. Now, lastly today, small one, perpendicular axis theorem. Statement. Moment of inertia of an area, see, some area, random area here, about an axis passing through any point. There is no rule that that point is centroid or it should lie within the area. It can lie anywhere. Usually, I can say it here. Why I take outside? Because otherwise it will spoil the sketch. If I mark the area here all, it will spoil the sketch. So I will take outside. That's all. That to show that this point O can be anywhere, but very important, in the plane of the area. Passing through any point in the plane of the area and perpendicular to plane of the area means about an axis. See, about an axis which lies anywhere, which axis passing through any point, say O, any point O, lying in the plane of the area, and axis is perpendicular. See, this way. I cannot show it here. Perpendicular. Perpendicular to the plane of the area is equal to sum of moment of inertia of that area about two mutually perpendicular axes. Mutually perpendicular axes, I should write, not axis. Perpendicular axis passing through that point and lying in the plane of the area. That means, see, if you want I about this axis, see, you write a note, mark any point O in the plane of the area, any point. Okay, we write outside just to see that sketch is neat. See, then through that point, you imagine axis. See, this is X, OX. See, this X and Y are not centroidal axis, random axis. Centroid means G will come. See, OX and OY. OX and OY should be mutually perpendicular. Very important. Mutually perpendicular. And they should lie in the plane. So what you do? OX and OY in the plane of the area. OZ here. See, I am showing this way. If I show this way, it actually, three-dimensional. It is actually like this. I cannot show here. See, how I can mark that one? So when I show this way, it is this way. Okay. Then I about OZ, that the perpendicular axis, equal to sum of moment of inertia about these two mutually perpendicular axes. 1 minute. Okay, you write. Or suppose you take a point O here, any point O here. See, this is OX. This is OY. This is OZ. Okay, then I about OZ equal to I about OX plus I about OY. Anywhere you can mark, but for proof, I will take this one. Okay, now lastly proof. Not a big one, very small proof. I'll finish that one now, proof. Single stretch, no pausing. Because why? Very, very simple. See, some statement you are right. Always when I prove in the class, see, in the notes all I will write the statements all. When I do in the class, what I dictate, you are right. Consider an area, random area. Consider any point O which lies in the plane of the area. Then consider two axes, OX and OY, OX and OY, which lie in the plane of the area but mutually perpendicular to each other. Okay, then consider another axis which is passing to the point O but perpendicular to the plane. I can't show it. I'll show this way here. See, Z. Okay, then this much statement you write. Then write, consider any elemental area dA. Let the let dA, let this is perpendicular distance from dA to OY axis, X. Perpendicular distance from dA to OX axis, Y. Now, also, see, OZ is here, see here. And also, see, this way. Why this way? Because, see, your axis is here. From here, perpendicular distance Z. Z. Remember that Z is radial. You can make a note, radial it is. With respect here, our coordinate system, it is radial distance. See, from XX, Y. From YY, X. From ZZ, see, perpendicular distance is Z. You write this way. Then write, after all this statement, then, right here, then by perpendicular axis theorem, I about OZ equal to I about OX plus I about OY. This is to be proved. To be proved. Okay, we'll prove now. See, first right. From basic definition, actually very simple definition of moment of inertia, right? I about OX equal to dA into y square, sigma of dA into y square. This is told thousands of times for you. Then, comma, moment of inertia about OY equal to sigma of dA into x square. See, I about OX is dA into sigma dAy square, sigma dA square, and I about OZ equal to sigma of, see, if you want about this sigma of elemental area dA into Z square. Some people write R, radial distance. Okay, Z is okay. Now write here. Therefore, I about OX plus I about OY equal to, see here, sigma of dA into y square plus sigma of dA into x square, or equal to, see, dA is common here, you can take outside, it is dA common sigma of, see, when both are common you can take outside, sigma dA into, I will interchange here, x square or y square plus x square, okay, y square plus x square, y square, right here, but y square plus x square equal to z square. Why? Pythagoras theorem. See here, y square plus x, this is x means this is also x only, y square plus x square equal to z square. Therefore, I about OX plus I about OY equal to, just now you got dA into sigma y square plus x square, which is equal to dA into sigma of z square, which is nothing but, see there, nothing but I about OZ. Yes, therefore IOX plus IOY equal to IOZ. Therefore, right here, perpendicular axis theorem is proved. Okay, over. That's all, simple proof. That's all. Today I will conclude the class now. Next class, very important. I will go for radius of, I have not decided still what to do. Some standard cases are there, that is regarding moment of inertia of rectangle, triangle, or I may take up that one. Radius of gyration, I may tell it later. Okay, I will decide tomorrow. So, class is very, very important. Today's class also important only for that matter. Okay, thank you.